don't mind. I think the faces are not recorded if you're worried about that. So we're just recording the screen share. So today we're gonna talk about functional modeling with PRIZ Innovation Platform, or how we start to call it PRIZ Innovation Hub, because there is more things to come and more releases to come, and it becomes kind of a hub. And kind of, as you can see, we renamed it a little bit, and we're saying it's an infrastructure for continuous problem solving and innovation, because it's a collection of many tools that build up the whole infrastructure. Now, functional modeling, and like any other presentation, we start with a quote. And in this case, the quote of Albert Einstein: "Any fool can know. The point is to understand." Now, this is where probably functional modeling help us a lot in understanding our own system, our own infrastructures, and take it further, even further than we can think about. Now, first of all, what is functional modeling in general? Well, functional modeling is a problem-solving tool, first of all. It helps us to model the problem, and that's a very important piece. We're modeling the problem, not necessarily the system, but we're modeling how that system, given the components and given the complexity of that system, can create the problem or the symptom that we look at, right? So functional model helps us to model the problem, and as a result of that, we can identify the most problematic and most functional components, and then work on the right component to solve the problem, to improve the system, to make things more efficient, and so on. Now, the key things that it actually allows us to do, first of all, like any other tool in the system that we have in PRIZ platform, it helps us to learn how the system works. If you remember from cause and effect chain, it's kind of the same story. We laying down that diagram, it helps us to understand how the system works. Even though people know very well how, or they think that they know very well how it works, you usually go into so much details that you kind of surprised even though you're the owner of the system. As a result of modeling, as I mentioned, we're defining the functional rank of the component. That's a very important piece to understand which component is contributing the most to the product, to the eventual product. And we will talk about what the product is. Define problematic rank. It's kind of the opposite direction. Which component contributing the most for the problem that we've seen, or the symptoms that we're seeing. Now, as a result of that, we can solve problems and improve and make the system more efficient with a focus on the most functional. So improve, take the most functional components and make them even more functional, and take the most problematic and potentially remove them or improve them. And by doing that, we improving the system overall. As we like to say, we basically able to impact things that matters, right? Don't work on things that don't impact the system at all. Work on things that matter. And by the way, stop me at any point if you have any questions, no problem. Now, what's the process of functional modeling overall? First of all, we need to describe the system, identify and describe the system. And what that means, before we start modeling and charting something, we need to understand what is it we chart, what is it we're trying to analyze. And especially it's important in a larger and more complex systems where you have many different steps. Of course, you can look at the entire factory that builds whatever computers, right? And think about it in that way, but usually it's not helpful. Usually problems become in a smaller systems or subsystems of that gigantic infrastructure. So we need to identify what is that system that we're trying to analyze. and by basically describing it within yourself, within the team that you're working with, and so on. Now, that will help us to identify what the product is. And it's probably one of the most important steps. And frankly, probably most challenging steps to identify what is the product of that particular system. And we'll talk about the product in a moment. Next, we identifying and describing the components of that system that belong to the system and super system components. And these are very similar to components, but they either don't belong to the system. And again, we will dive into the details into that, or something that we don't want to change, not willing to change at all. Then again, identify and document the functions between the pairs of components. That's where the functional language comes in. The functional description of the system comes in. By doing that, we mapping the functional modeling, the functional model to model again the problem, right? To model the symptom that we're seeing, and then calculate functionality and helpfulness of components, and then move forward from there. Now, what is the product? What is that thing that is a product? In general, if you take any system, big or small, the product is something that the system was built, designed for. And I'll pause here for a second. Who can give me an example of a product in a car, for example? What is the product of a car?
The wheel is steering the car.
The wheel is steering the car, but is that what the car was designed for? What is the main function of the car?
Driving, but it is essential that it drives into the direction I want it to.
Right.
Objects.
Right. So it's objects. In case of a car, if you think about it, the car built to move something, to move cargo, to move human being. We like to think about it as to move the driver, people, right? Now, how it's all done, that's a different story, but the main function of the car is to move people or things, right? So for the purpose of a car, the product becomes the human being, for example, right? Or if it's a truck, then it becomes the cargo or the goods that it's moving, and so on, right? So what the system is designed for doing. Now, most engineering systems, and in fact,
Alex, sorry for interruption. So product is not a part of the system?
No, product is what the system built to change the parameter of. So, for example, product. If we again, let's go back to the example of a car and a human being. We'll talk about the function itself. Function is something that when an engineering system or a component, for that matter, changes a parameter of a product, right? So in this case, an engineering system, the whole engineering system that we're analyzing, changes a parameter of the human being, for example, means, and the parameter it's his location or his speed, or if you will, if that car is some cool Ferrari car that he is, makes him happier to drive that car. Whatever the function of that particular car, that becomes a product.
Now,
right?
you asked about if a product belongs to system. Product never belongs to system.
Okay, sorry.
Always separated from system.
But object belongs to the system, correct?
No.
So object should be part of the system. That's what you want to move.
No, it's not the part of the system. Today you move Yuli, after that you move Lita, after that Alex. No.
But the car stays the same, right?
Yes. Car is built to move something. This something is a product that doesn't belong to system. Car exists without product. It is built. How to find product? To have a look on what main function is. The washing machine built. What is a product of washing machine?
T-shirt that is clean afterwards.
Clean surfaces.
Surfaces.
That's
Surfaces.
So probably the product is surfaces.
Clean surface is a function. This is the main function. Clean surfaces, object surfaces. This is a product. Clean surfaces.
The
Parts.
surface, clothes, or if we look at the washing machine as something that removes dirt, right? Then the product becomes the dirt.
Mm-hmm.
Same system, by the way, can be same system might have different product, depends on what is it you're trying to analyze and how you're trying to analyze it, and which direction you're looking at that system. Again, back to the example of car, if we're trying to affect how much pollutant, how much the car is polluting, right? The product is probably the pollutant, potentially, right? It emits pollution. Now, what is it we're trying to improve? Where is the problem that we're looking at? So if we're trying to improve how we move people, then people are the product, but they outside of the system. If we're trying to reduce pollution from the car, then probably pollutants, the particles that it emits, might become a product, right? If still the same system, the product is different and the analysis is going to change completely.
But this is some specific case. In general, the product is a human being, is a cargo or something that should be moved. And if you build full function, you will also see pollution and CO and so on. But if you want to shorter the model, you can say, okay, so my product is a CO. Oh, my product is I don't know, the hot air near the engine, and so on. But generally speaking, this is what our system is built for. Okay.
Mm-hmm.
Does it clarify? Again, this is a very important part, probably one of the most important pieces in this entire functional modeling, and happy to spend more time on this if there's any more questions.
We will see it on exact examples.
Mm-hmm.
Okay.
All right, let's move forward. Again, stop me if you need to. So again, that's the example that we just discussed. For the car, right? What is the purpose of the car? And that's exactly what we just discussed. It is to eventually move people, and I should have probably dive into this slide before. But in case of a car, if we're trying to, for example, analyze how well it performs for the person that it drives or moves, or whether it's a cargo or not, the function is to move, right? Or if it's this car, like a Ferrari, it could be make people happier, right? It could be also a function, but still, in both of these cases, the product is people. Okay.
Yeah.
Now, let's talk about components. So the same car that we just talked about, what could be components? And I'll ask I'll ask the audience, what are the components?
The engine?
Yeah, it could be tires, brakes, the body, the engine, anything that is part of a car, and what's important, we willing and can change, right? So anything that is part of a car and not the person who is moving. Now, the other piece is super system components. What are the super system components? Again, it's something that does have an impact on the system, but doesn't belong to the system, or we don't want to change it.
The street?
It could be the street. The examples that we have here is air, could be pollutants, right? Pollutants we may or may not want to change. Again, that kind of a game here. It's a rain, it's a street, like Lita said, the road, right? Which is absolutely correct. And probably there's more things to it, but these are examples of the super system, right? Now, it could be that we decide, you know what, the wheels technically are part of the system, but we don't want to change them, right? We're happy with them, we don't want to change them. We can make them as a super components, right? And that's a game that we're trying to play. If you'll see an example that this whole functional modeling is kind of it's a little bit of a game when you're playing with the system, playing with the components, see how it all works out, right? Now let's go to the functions. Once we have all of the components and the super components and the product on the board, now we can start defining the functions. And functions are interaction between components, and that's the important piece, that result in parameter change of another component. So for example, if component
Alex, sorry for interruption. Do we always have to change parameters? Maybe
Yes.
the function of the system is to keep them constant, for example. Do not change, prevent any changes. It also can be a function.
No.
Then preventing changes, it means that it puts these parameters back to its normal, for example. Right? It changes the parameter of some other component that causes the prevention eventually. Right? If
Julie,
nothing
this
changes,
is. I'm sorry. Yuli, this is just definition. We cannot discuss it. This is definition of function. If I'm dreaming about a glass of beer, no function, no parameter change. I drink beer, I change the volume of. You cannot say the keep volume stable is a function. No, it's not a function.
For example,
We can
aging of people. We want to prevent aging of people for some reasons. So we want to keep some functional parameters like blood pressure, pulse, etc. constant. We don't want them. We want to prevent change.
Right, but how do you normally do that? How would you normally do that? You would
change parameter, yeah.
You change parameter of the blood chemistry, right? Or you change parameter of the blood vessels. You make them more flexible to prevent.
I see. Oh,
right?
Got you.
So in order to keep parameters, you need to change parameters of something else in that particular scenario, right? Or in many other systems, and there's other analytical tools or problem-solving tools that have a definition of preventing function or for example, preventing function. What does it mean, preventing function? It means that something happened, some parameter changed that you don't want it to change, and preventing function is actually putting it back to where you want it to be, right? It's still, if parameter doesn't change, then you can throw away that component altogether. It doesn't do anything, right? And it is important to understand what parameter is changing, because realistically, if the component doesn't do anything, it just eats money. For example, I don't know, it's a component that plugged into the outlet and eats electricity, and that's all it does, why is it there?
No, but this is a function, just only harmful function.
True. True. Okay, so in case of when we're talking about functions, we're talking in terms of functional language. And what does it mean? Again, I'm going back to that. It's the when one component changes a parameter of another. So, and the arrow usually goes from, in this case, component 2 is changing some parameter of component 4, right? Same applies for the product. Same applies for a super system. And by the way, both ways. The only difference between the regular component or auxiliary functions, or super systems, is that super systems is not something that we can affect or change, or not willing to affect or change, right? Any questions here? Okay, let's continue with the type of the function. There are 4 different types of functions, and they can be represented in pairs, right? So first of all, a useful function is the function that a particular component is built for, and it's performing as expected and creating that useful function. For example, I don't know, the engine is spinning the wheel eventually, right? That's a useful function that it's been built for. Now, on the opposite, and on purpose, we looking at this as 2 contradicting functions, useful and harmful, right? So on the opposite, if we're talking about the engine itself, it has a harmful function, like heating up the air around it, or heating up the water and the water tries to cool it, right? So that would be a harmful function. It's not something that we really want. Okay, there are also useful-ish functions that's called excessive and insufficient. For example, let's take the same engine. It spins the wheels, but it does it too fast for whatever reason that we don't know what that is. That would be excessive. So it works. It produces that torque too much, more than what we expect, more than what it's been built for. And on the opposite, we have the insufficient. You know, the engine gets a certain amount of fuel, but it actually doesn't produce the same torque that it's supposed to, or the same power that it's supposed to. That would be an insufficient function. Again, 2 contradicting sides: excessive, insufficient.
But why do we need them, 4 of them? Why it's not enough to use just only excessive and insufficient? Because if it's excessive, per definition, it can be harmful. Insufficient, it can be harmful. It performs properly, that's useful. That's it. Why do we need 4?
So harmful, for example, you have, it's all about what the system is built to do, right? Back to the engine example, it's built to spin apart, to turn apart, to spin apart, to move apart, right? Great. That is what it's built for. That cannot be harmful by definition. Now, how it performs, this is where the definition of excessive and insufficient comes in. The harmful is something that is a byproduct of that component, something that it's there, we don't want it, but it's there because of physics, because of how it's built, because whatever the reason is, right? And this is where that distinction is important. It is performing, but for example, not well enough.
Useful, excessive, and insufficient, they all 3 are useful functions. You have water for washing hands, but you threw much more water than you actually need to wash your hands. So you use excessively water, but it is still useful. And you have a heating system of water And this system is heating insufficient. You should heat it because you heat everything outside and not only water. And due to interaction of water with, I don't know, metal parts, tubes, pipes, corrosion occurs. And this is not useful function. This is a harmful function. This is again, these two types are useful, group of useful functions and harmful function. And within the group of useful function, could be excessive, it could be insufficient. And we know a lot of situation in technology and processes when we have to do something more than necessary and sometimes less than necessary, because otherwise the process is not working.
For example, another example to have a pump, right? A pump is built to pump water from one place to another. And the useful function, useful definition of a function would be it pumps water with the speed and the pressure that it's supposed to, right? What it's built for. But in general, it's built to move water. Excessive could be it actually maintains too high of a pressure, right? That would be an excessive function. Or not enough pressure and basically not enough flow of water. It would be insufficient water, insufficient function. So it's not moving the water fast enough, right? It's still what it's built for. It's built to move water from one place to another. But does it do it well enough, or working too hard?
And of course, we need these 4 types of function in order to make calculation, make ranking of different functions and ranking of different components. They all have different score. Okay? All these functions have different score.
All right. Okay. So before we continue further to the example, if there is any other question, I'm happy to answer. All right, let's jump to the example. So I already created the project for our use case, and to save some time, I already have the description. So we created the tool in here, and the functional model is available in here by adding a new tool. So it's already created. I added the description, and on purpose, the example we're trying to discuss here today is not a technical system at all. It's a managerial system, right? And we chose this example for the purpose, for a reason that functional model is not only for engineering systems, not only for technical systems or like a car or I don't know, a piece of machinery. It's also good to analyze managerial problems, because anything can be looked at as a system, eventually, a system of people in this case, or it could be people of a system of, I don't know, natural components, right, that we can and willing to change. So in this case, we're looking at the scenario where we have a group of engineers at some company. Again, it's a real case, but we changed the names. But it is a real case from not that far past. In some company X, product enterprises, there's a team of engineers that is consistently underperforming. And underperforming, these are software engineers. The product that they're creating is the actual product. It's a piece of software. The quality is not good enough for that particular case. So they're working on improving the stability of the product, improving the test coverage, reducing bugs, and so on and so forth. That's their initiative that they're working on. And it's not going well, to be honest. Now, this group is consistent. Now, what does it mean not going well? It means, yes, they creating the test coverage. Yes, they creating the automated testing, but on the way, they also creating more bugs. So they pretty much overwhelmed with bugs. They're trying to fix them. They introduce more and so on and so forth. Eventually, the quality of that product, that piece of software, suffers. Okay. Now, the group of people, again, the names are fake, are split into several groups. Actually, I'll put a group. So I put here group 1, group 2. So group 1 and group 2, they've been split here on purpose because they're very similar in their knowledge, in their performance, and in what they tasked with. So Jane, Eve, and Mike, they fairly experienced. Also from a business knowledge perspective, as well as engineering. Nancy and Nick in here, they fairly new to the company. They're still pretty good engineers, but they new to the company. They don't really know the business case too well. And then there is a Sam, that person who's been with the company for a very, very long time, but he a little bit lacking the engineering best practices, if you will. Right. Also, there is an engineering manager involved that manages that group. As part of the whole, the rest of the company, there's other engineering teams, product managers, executives, and what we call the other teams, right? They part of a system, of course, but we just group them as one to simplify this case, the other teams, right? And of course, there's a client. So in this particular case, if we're talking about the quality of the product that this group of people building, that piece of software that group of people building, what is the product? What you can think about as the product? So again, what worries us at this point in this particular problem is the software that they're building, right? So if we want to improve how the quality of the software, the performance of that software, how well it's built, how well it performs, by definition, the product becomes the product that they're building, that piece of software itself, right? So let's just dive into that. When you start with a functional modeling, just a completely fresh, new instance of the functional modeling, this is the picture that we're getting. We're getting some placeholder. And in this particular case, the product is always marked as this orange oval shape. And the product, again, it can be only one product. We can change it around, and then the product will become something else. And by definition, the previous product will become one of the components, right? We can have several different regular components and several different super systems. There is no limit to that. So let's say we talking about this software that group of people is built, right? Now, if we're going back to this, and let's start putting components in place. So on purpose, we split these group 1, group 2, Sam, engineering manager, and so on, right? So let's say that's the group 1. Oops, why is it capital? Group 1. This will be group 2. This will be Sam, that one person, or group 3, doesn't matter. Let's convert that to a component, and that would be the manager, engineering manager. What else do we have here? We have other teams.
Could you be on mute, please?
Yeah,
Guys.
I muted. I muted. We have other teams. What else do we have? We have the client, right? So client, we can't really change them. We can only manage them. So by definition, the client becomes the super system clients. So that group of people were working on tests, like automated tests. So that's another component that we're changing a parameter of tests. What else? The software is basically built on a bunch of code. So that would be the code. What else? Do I miss something? I
Bugs,
think we can.
bugs.
Right. And we have bugs that affect the system, of course. Right. So we threw these components on the board. It's all good. Now let's start mapping the functions, right? So the code is basically the code is creates the software, or we can call it supports the software, right? And again, at this point, it doesn't matter. You don't have to think about the usefulness or harmfulness. It's like, what is the function? We can map types of functions later. It's going to be actually much easier to map later. Now, of course, the clients are using the software. What is the function? What is the function and what is the direction of the function between client and the software? Who is changing parameter of who? If you think about it, if the client uses the software, client does not change the parameter of the software. Lita, you muted if you're trying to talk.
The software changes the parameter of the client.
Right.
The client gets his work done.
Informs.
Sure. We can call it in a different ways. It depends on how deep we want to get into this interaction. If we want to get really deep into that, then it could be several functions. It could be maybe, you know, the software changes client's mind, and then as a result of that, the client does something else and so on. It depends on how detailed we want to get to that, right? We can get to the cell level of detail, but do we need to? In this case, let's simplify it for now. And let's say it informs. It's some software that, I don't know, a search engine, right? Literally, it informs, right? Now, what about bugs? Bugs are breaking the code pretty much. And in this case, we can immediately say, well, it's harmful. There is no question asking here, right? Unless somebody have a different idea. I don't know any others. Okay. Now, knowing these groups of people and how they perform, group one and group two, well, all of the engineers, since this is their main initiative at this point, they building tests, right? They create tests. This group of people also create tests. And Sam also creates tests. Now, as we talked about, every one of them is inadvertently, when they change in code, they potentially also create bugs.
Pardon?
They create bugs when you changing code.
Mm-hmm.
Well, there's actually two things. They fix the bugs, which is good, but in some cases they also create bugs, right? They're changing something that they didn't know they can potentially introduce a new bug, right? Of course, it's a harmful function, no question asked in here. Now, group one and group two, some of them more proficient actually, and I want to switch them around. Oops, I want to switch them around a little bit. Come on, I want to switch these around. Group one is a little bit more experienced. They know more about the system. They actually introduce much less bugs, but they also fixing them, right? So they fix the bugs, right? Sam also fixes the bugs, but know how he performs. He also introduces new bugs, so he creates new bugs. And again, in software world, that's kind of normal. You're changing one thing, you have a very high potential, especially if it's a complex systems. You have a very high potential to break something that's unrelated, especially if the system not built very well and so on. Now, what about the manager? What's the function of the manager? The manager directs all of them, right? So directs, he also directs Sam, and so on. Sam is, on the other hand, reporting back, reports back to the manager. Well, all of them reporting back to the manager, right? That's the interaction between the manager, and the employees. So until now, nothing is too crazy. Now, this group is also tasked with writing new features. So it, let's say, create new code, and in this case, creation of new code is literally creation of new features, new functionality, and so on. Right? What about other teams? Other teams, if we're talking about like product managers and other engineering teams, or even the CEO of the company, first of all, and that's the situation, that it's a true situation, the clients were informing the teams about different problems and stuff, right? Basically complaining, pretty much. Right? Now, other teams were also contributing to the code. So that's just the situation how it was in the company. They were contributing to code and writing new features. So you see how slowly but surely this whole thing becomes more and more complex, and all of these interactions between components, they're not very clear at first, right? Now, since they building code and they directly working with the client, they're doing it very fast. They actually create bugs as well, right? That's of course harmful, no question asked. And the other teams, since clients complaining, and the other teams pretty much complaining to the managers, hey, do something with it. Also, let's say, inform. Okay. Now, Sam, being very mature in the company for a long time, he knows every in and out in the company. He helps other people, other groups. So he helps them, let's say, train and support for the other teams, because the other teams, they outside of the box of the product that we talking about, they're still contributing, but they kind of outside of this particular group of people, so they need support. And on the other hand, they inform Sam, since he is the most knowledgeable of the system, they asking him a bunch of questions, right? Inform him of a question that they have, right? Let's all organize it a little bit. So as you can see, this becomes potentially, and that's a simplified model of it, potentially somewhat seemingly simple thing, just a small group of engineers creating one piece of code. It's actually pretty complex, right? Now, let's look at them in more details in terms of the quality of the functions that they do, right? So as I was mentioning, this SAM have but somewhat bad engineering practices overall. He's a good person. He knows a lot of things in the company, has bad engineering practices. So basically when he fixes bugs, he doesn't do it very well. He's not very detailed. Okay. Now, of course, when he creates, and as part of that exercise, fixing bugs and writing code, he creates bugs as well. That's of course harmful. Since all of these happening, the manager needs to have much closer view on him. So he needs much closer hand-holding with Sam and directing him much closer. And of course, Sam reports to the manager much more, right? Now you start seeing how these things, you analyze every interaction between different components, every function. Is it useful? Is it actually happening too much? For example, in that particular case, the manager was spending like hours a day with Sam every day, just to keep him intact, right? Now, the other team asking for support, and he gives them support, but he doesn't do it very well. He struggles with explaining, right? Again, struggles with documentation, struggles with explaining, and so on. This group, what do we have? It creates bugs. Creates bugs, creates code, fixes bugs, writes tests. What else? This group of people, being a little bit less experienced, they creating tests, they're doing the best they can, right? Also, since this group, the other group of people, since they're contributing to the code, it would be ideal for them to write tests as well for the code that they do, but they're actually not doing it enough. Nobody wants to write tests. It's not something that you're willing to do, but it's a necessary evil. Let's put it this way. Okay, and I think overall this is where we are. Questions until here about the process? Oh, the other thing that I forgot, why the tests are even there. The tests are testing the code. The test is testing the code. That's what it's there for, right? And for the test that it does, it is built for. It's doing it pretty well. It's automatic. Everything is fine.
Alex, I would add an opposite function also. Code informs test, or test informs person. I don't know.
We could.
Okay, up to you. Yeah.
We could do that. It depends. Yeah, then again, I don't want to overcomplicate it at this point because test informs all the groups, including the managers, including the other groups. The code doesn't inform the test necessarily. It may. I'm afraid that we're just gonna dive into too much details. Too many details in here. Okay. Now, let's look for a second at the ranking that it creates. right? So in the ranking, this is the automated calculation. And as we talked about, there's a functional rank. So basically, the components that contribute the most to the quality per se for the product, for that piece of software. And then there is a problematic rank of the same. So for example, components that actually creates problems in that software. Okay. Just for an example, we can present only the functional ranks or only problematic ranks just for convenience, or look at them both, right? As you can see, the most problematic component, and in this case, it's a person, it's Sam, right? Now, normally you would say, but he still has, by the way, pretty high functional rank as well. He does a lot in the company.
If I can ask, where do those numbers come from?
These are calculations based on a model that's been built. Okay. And the ranking are from 0 to 10. You can't go over 10, you can go less than 0. It's a relative numbers within that range.
The ranking is calculating, for instance, functionality of component depends on how far you are from the product. Your radio in the car is very far from moving car, and the problematic is calculated from the presence of harmful, insufficient, or excessive functions. There are special rules, and you can do it manually, but it's not trivial. Computer did it. Yeah.
Yeah, and by the way, there's many formulas. Not many, but there are several formulas for that calculation. We have our own, for example, right? They very close to each other conceptually, but there are some different variations in that formula. Guys, I know we getting close to the hour, and I apologize that we're getting over time, but if you have time, happy to have you here. So the next question is, what do we do? Of course, we're seeing that Sam is the most problematic, and normally managers will say, well, fire the guy, right? There are two problems with that firing the guy. First of all, he does have a lot of contribution with all the problems that we have in the system as a result, resulting from Sam. He does have a lot of functionality, right? Second piece, he is a buddy of the CEO. We can't really fire him, right? So what do we do with that, right? And for the sake of an argument, let's save that. I'll take just a screenshot of this and save it in conclusions for now, okay? Just so we have the record. Now, what can we do with that? What can we do to make Sam more useful, less harmful, except firing? If you're looking at this model and what he's doing and how he does things.
Best thing he does is reporting to the manager.
Yeah, I have to say he does it pretty well.
But too much, isn't it?
True, but you can't. I mean, if he's not performing well, you can stop talking to him, right? But what is the most harmful things, right? The one that comes into my mind, at least, is he creates bugs, right? But how can we make him not to create bugs? He needs to stop touching the code, pretty much, right? Even though he's an engineer, for now, for now, let him stop fixing bugs, right? So let's do that. Let's just remove him from that equation. Now, he doesn't fix bugs. He doesn't create them, right? writing tests is fine, right? Now, as a result of not creating bugs and not fixing bugs, not creating bugs, not writing new code, he basically all of a sudden has more time to concentrate on something else. So hopefully this function becomes more useful, right? He will be much more sufficient in here. Okay. Now, let's look at the ranking, how that improves. All of a sudden, his functional rank didn't improve, but his problematic rank gone down. And all we did, we actually asking him to do less. Right? It's a little bit counterintuitive in this case, but we actually we ask him to do less work. Yes, there are other problems that come up as a result of that. So other teams, they're now more problematic. That's a separate problem to solve. But speaking about Sam, now, how can we make him even more efficient, more useful, right? If he's doing training pretty well, and he loves to talk, as you can see in here in this interaction, let him train and support other people as well within the group, right? Train and support, including even manager. So that would be reporting. Let's do another function here. Trains the manager and so on, right? Go back to ranking. All of a sudden, Sam's function is pretty damn good, right? Still, the problematic rank is there, but it's much more improving, right? And so on. So if you remember, I mentioned this is becomes kind of a game to play within this model, and game to play in this case with people. How do you improve? Because normally what people would do is say, you know what, let's try something. Does it help? And a couple of months later, no, it doesn't help. Let's try something else. Does it help? Again, a month or a couple of months later, no, not really. Maybe improving, but not enough, right? This makes that trial and error a little bit faster and smaller. And again, if he's performing well enough in these areas of being the trainer, of directing people and helping people and supporting them, great, then probably these interactions needed less. So this just becomes a normal directing for the manager. He doesn't need to spend hours and hours with that person. And the same the other way around, right? Let's look at the rank. All of a sudden, Sam is just useful, right? Now, we can go through exactly the same exercise with other components as well. How can we change their functions? The component is not changing. As you can see, Sam is still the same Sam with the same experience, with the same brain and the same engineering practices that he had. But changing what he does, changing his title pretty much within the system changes how he performs. Okay, and for the lack of time, I will stop here for now. For any questions, any concerns.
Guys, I'm fanatic of functional modeling. This is the strongest thinking tool. Helps us think to create model. You know, like you have some problem with equipment, you open scheme and you see how it is connected, and you are starting to look for problematic parts. Here you build functionality of your system, and this is just fantastic. very strong. Try this, and feel free to call us if you need some help and explanation. It's very strong tool and widely used for everyone.
A couple of more examples that we have in here is, this is also from, it's a real example from the past. We're analyzing, I think we discussed this in one of our, this use case in one of our webinars before. It's a wafer breaking, or no, that's actually cleaning of a wafer in microelectronics manufacturing, and the model looks like that. Eventually, the process is the same, and drawing conclusions are of course different because it's the different systems. And this is a technical system, very technical system. There's no people involved at all, right? Another example, probably, I don't remember if this one has a functional model. Yeah, it does. Again, also related to the same industry, microelectronics. When wafer is breaking and we're analyzing how can it break, much simpler model, right? But the process is the same. We're defining the components, we're defining the functions, and we're trying to think how can we create the problem that we see, that we observe, or the failure that we observe within the system, on this case in the wafer, on the product. How can we create that problem? How can we create a symptom that we're seeing? This is what we're trying to model. And this is very important. Not just how the system works or supposed to work, but how do we model the problem? That's the important piece, right? And in this case, how do we model the fact that the product, the software that this group of people building, is not up to standards, is not quality product, right? And how can we improve on that? Any questions until now?
Can you send out any PDFs or anything of some of these modeling examples?
Right. So when you go into reports, first of all, I can of course send out as much like all of them as we have. Now the report is including everything, right? That's the conclusion. This is what that's the screenshot. Sorry, that's the screenshot that we put in. That's the current status of that model and the ranking and everything. With SAM being on top in this case. And that's the part of the conclusion. We didn't write anything additional in there, but that's the initial picture that we had, right? Is that the PDF that you were referring to?
Yes, that would,
Yeah, we can send it out for sure.
that would be
And we
great.
can send out a bunch of examples, other examples as well.
Thank you very much.
I will do that. I'll put a note for myself. And again, if we going back to a couple of other examples, let's go to the wafer cleaning. If you go to the report, again, it's not only the functional modeling that has the information in the report. It's actually everything. Let's go back to down to everything that we used. So in this case, we used several tools, and some of them, of course, one of them is functional model, right? And it's all self-documented. The process is there. Who worked on it? What's the order? What's the conclusion out of that? And so on. And we 10 minutes over. My apologies for that.
Guys, do you like this functional modeling? I don't hear. This is so cute.
I think
do
this
that.
is really cool. For example, for storytelling, if you want to write a real good story, you need everybody interacting with each other and with things. And that could be really good to come up with the right idea.
Exactly.
The most interesting piece, and I've seen it so many times, where group of people, group of engineers working on a system. Again, I'm coming from software, so they working on a piece of software, potentially not very complex, but they all think that they know the software really good. When you start analyzing them, and within the same group of people that consider the expert within that system, it appears that they don't know as well as they thought they know, right? They didn't think about some interaction between components. They didn't think about that, oh, wait, there is something changing here that actually has an effect on something else, right? They don't look at, and it's normal. You can't have everything in your head at once. It's really hard, especially in complex systems. This modeling, especially when you're working within a group, it actually opens people's engineering, opens the eyes of the engineers.
Yeah, that's why I was asking for examples. I think it's really good to take a look at, and I'd like to show some other people.
Yeah, for sure. I will send as many as we have.
You know, one more interesting point. I'm conducting lectures in university. I created a course, engineering thinking. You know, we teach people, students, physics, chemistry, mathematics. We typically don't teach them how to think. And what's interesting, a functional model looks like a very difficult tool, but they pick up it very, very fast. They get inside. I have to say, I saw a couple of examples where people, in order to formulate, to state the problem, they created functional model. This is a very, very useful and universe too. This is a way to understand how your system operates. And until now, I don't know other tools to learn better how a system operates.
And yes, it does require some level of getting used to that thinking of a functional interaction, right? Because usually people think, you know, the function, quote unquote, like we talked about, clients using the software, right? So in majority of cases, the function is actually inverse from what people normally used to think, right?
Mm.
So yeah, it does take a little bit more than just it requires a little bit of training, a little bit of getting used to that different way of thinking, right? But you know, you're doing it once, even, and here's the interesting part, even if you're doing it incorrectly, or somebody doing it incorrectly, it's much better than not doing it at all, because it makes you think about the different components, right? That's already 100% better than nothing. Because how people solve problems today, unfortunately, is they sit there and they think.
Now also look for something on the sailing. I don't know why people like sailing.
When engineers tasked with the problem, their typical answer at first is, let me think about it, right? But what does it mean, thinking about it? It's literally thinking about it. But a week after, or the same evening, he already forgot to think about it. Right? There is no outcome from thinking unless he has a solution straight away. That's a different scenario. But thinking about it, you need to have some mental model in place of how you're going to think about it. It could be on a board. It could be on a piece of paper. You need something, right? So this is where we're trying to provide that something that will help people to start working with themselves, pretty much. All right. I'll stop recording for now and open for questions.